Hello students, today we are going to continue about network layer protocols. As previously we have discussed about IP datagram format and its characteristics. In continuation with that, we will be discussing a few of the concepts like fragmentation, maximum transfer unit and so on. Okay, a datagram, it can travel through different networks. Each router, it decapsulates the IP datagram from the frame when it receives it and processes that particular datagram, and then it encapsulates it in another frame. The format and the size of the received frame, basically it depends on the protocol which is used by the physical network through which the frame has just traveled. Okay, and when you just consider as an example, if a router connects a LAN to a WAN, it receives the frame in the LAN format and sends the frame in a WAN format. Okay, that is why the format and size of the received frame depend on the protocol used by the physical network through which the frame has just traveled. Okay, and also the format and size of the sent frame depends on the protocol which is used by the physical network through which the frame is going to travel. Next, let us discuss about maximum transfer unit. Here, every data link layer has its own data format. Okay, so one of the feature that each format is going to consider is maximum size of the data or the payload. Okay, that you can encapsulate it between a header and a trailer. Now when a datagram is encapsulated in a frame, okay, the total size must be less than the maximum size. Okay, and since because hardware has put some restrictions and used whatever the network which is being used here, it has its own restrictions whenever it is moving from one layer to another, or sender to destination or a receiver. Okay, there could be a variation in the size of the datagram which has been encapsulated. Okay, so it has to be less than whatever it can handle. Okay, consider this is the diagram of a maximum transfer unit. Here the value of the maximum transfer unit differs from one physical network protocol to another. Say for example, the value of the LAN is normally it varies from 1500 bytes, but for a WAN it can be smaller also or it can be larger also. Okay, now in order to make that IP protocol which is to be independent of the physical network, the designers they have to decide the maximum length of the IP datagram, which should be equal to 65,535 bytes, as we have previously seen in the IP datagram format. Now this makes the transmission more efficient. Say for example, if one day we use a link layer protocol with a maximum transfer unit of that particular size of 65,535 bytes. Okay, that could be the maximum that makes the transmission more efficient. Okay, now however, like for other physical networks, we must divide that datagram to make it possible for it to pass through these networks. So we need to fragment. The process of dividing the datagram to make it possible for it to pass through these networks is considered to be the fragmentation. Okay, now when a datagram is fragmented, each fragment has its own header with most of the fields repeated. Okay, but have some are changed. Okay, now when a fragmented datagram may itself be fragmented if it encounters a network with an even smaller MTU. Okay, that is maximum transfer unit. In other words, we can tell it like this: a datagram may be fragmented several times before it reaches the final destination. Okay, now a datagram can be fragmented by the source host or even any router in the path. Okay, the reassembly of the datagram is done by the destination host, because each fragment becomes an independent datagram. Whereas the fragmented datagram can travel through different routes, and we can never control or guarantee which route a fragmented datagram may take to reach the destination. Okay, so it is logical to do the reassembly at the final destination, and even a stronger objection for reassembling packets during the transmission is the loss of efficiency it incurs. Okay, now when we talk about fragmentation, we mean that the payload of the IP datagram is fragmented. Okay, like most part of the headers, with the exception of some options, okay, must be copied by all the fragments, right? So the host or a router that fragments this datagram must change the values of the three fields in the IP datagram. If you can remember, we have something called as flags, fragmentation offset, and total length. Okay, the rest of the fields must be copied as it is, and the value of checksum must be recalculated regardless of the fragmentation, whatever you have done for each frame. Okay, and the fields which are related to fragmentation, as I told you, in an IP datagram, they are identification field, flags field, and fragmentation offset field. Okay, now the 16-bit identification field, it identifies the datagram. Let me go back to the IP datagram to show you the fields which are related to fragmentation. Now this is the diagram of an IP datagram format. Here you can see in the header, the second line, there are three fields which are mentioned. Those are related to the fragmentation, that is identification, flags, and fragmentation offset. Okay, this 16-bit identification field identifies a datagram which is originating from the source host. Okay, the combination of the identification and source IP address must uniquely define a datagram as it is leaving the source host. Okay, to guarantee the uniqueness, okay, uniqueness of the frame. Okay, the IP protocol uses a counter to label those datagrams. Okay, now once the counter is initialized to a positive number, basically it is initialized. Okay, when the IP protocol sends a datagram, it copies that current value of the counter to the identification field and increments the counter by 1. Okay, now as long as the counter is kept in the main memory, that uniqueness is guaranteed. Okay, now when the datagram is fragmented, the value in the identification field is copied into all the fragments. Okay, and the identification number, it helps the destination in reassembling the datagram once it receives all the fragments, and it knows that all the fragments having the same identification value should be assembled into one datagram. Okay, and the flag field, okay, there are 3-bit flags field. Okay, defines 3 flags. In the 3-bit, the leftmost bit is reserved, which is not used. Okay, in the second bit, you can call it as a D bit. It is called as a D bit. That is do not fragment bit. Okay, if its value is 1, the machine must not fragment the datagram. Okay, now if it cannot pass the datagram through any available physical network, it discards the datagram and sends an ICMP error message to the source host. Okay, now say if its value is 0, then the datagram can be fragmented if necessary. Okay, and here in the flags, the third bit is called as the M bit, and that is a more fragment bit. Okay, say for example, if its value is 1, it means the datagram is not the last fragment. Okay, there are still more fragments after this one. And if the value of that m bit is 0, it means that this is the last or the only fragment, okay, to pass. Now the 13-bit fragmentation offset field, it shows the relative position of this fragment with respect to the whole datagram, okay, and you can call it as the offset of the data in the original datagram, which is measured in units of 8 bytes, okay. Now I'll show you a picture of a datagram with a size of somewhere around 4000 bytes, which is fragmented into 3 fragments, okay. This is the example of a fragmentation. As I told you, it is fragmentation of a data of size around 4000 bytes, and it has been fragmented into 3 fragments, okay. Now the first fragment carries bytes 0 to 1399, okay. You can see in the diagram the offset for this datagram is 0 by 8, which is equal to 0. The second fragment carries bytes 1400 to 2799. The offset value for this fragment is 1400 divided by 8, which would give you 175. And finally, the third fragment, which carries the bytes from 2800 to 3999. The offset value for this fragment is 2800 divided by 8, which is equal to 350. Now consider the example of a fragmentation. Here the original packet starts at the client. The fragments are reassembled at the server. The value of the identification field is same in all the fragments, as that is the value of the flags field with the more bit set for all fragments except the last one, okay. And also the value of the offset field for each fragment is shown. And you also note that the fragments, though that is arrived out of order at the destination, they can be correctly reassembled, okay. And it also shows what happens if a fragment itself is fragmented, okay. Basically in this case the value of the offset field is always relative to the original datagram. For example, in the given figure you can see the second fragment is itself fragmented later, that is into 2 fragments of 800 bytes and 600 bytes. You can see that in the picture it is being divided into 800 bytes and 600 bytes, but the offset shows the relative position of the fragments to the original data, okay. Now if each fragment follows a different path, okay, it's obvious that like even if each fragment it's following a different path and arrives out of order, the final destination host can reassemble the original datagram from the fragments which are being received, okay, in case if none of them are lost, using some of the following strategy which I'll be discussing now. First strategy that it can reassemble, okay, is the first fragment has an offset field value of 0, okay. Divide the length of the first fragment by 8. The second fragment has an offset value equal to that result, okay. So you can easily see in the picture. Now the first fragment is like 0. When it is divided by 8, whatever is the value, the second fragment has an offset value equal to that result, okay. Next, divide the total length of the first and second fragment by 8. That is a third point, okay. The third fragment has an offset value equal to that result, okay. And continue the process till the last segment has its m bit set to 0. That is more bit value as 0, okay. Now let us understand the process with some examples as shown here. Consider a first problem. A packet has arrived with an m-bit value of 0. Now is this the first fragment, the last fragment, or a middle fragment? Do we know if the packet was fragmented? Now the concept is they are telling m-bit is 0. Okay. If that is 0, there are no more fragments. Fine. The fragment is the last one. Correct. So we cannot say if the original packet is fragmented or not, since that becomes a last frame or last fragment. Okay. So here they are telling that a non-fragmented packet is considered the last fragment. Okay. Now consider this example. Here they have given as a question that a packet has arrived with an m-bit value of 1. Is this the first fragment, the last fragment, or a middle fragment? Do we know if the packet was fragmented? Now its question is simple. If the m-bit is 1, it means that there is at least one more fragment behind that, right? So this means this could be the first fragment, or it could be the middle, or even but not the last one, because when m-bit is 1, it is telling that there is still more packets or fragments are ready to arrive. Okay, so we don't know exactly it is first one or middle one, and we need still more information, that is the value of a fragmentation offset, to tell where exactly the position or the which fragment it is. We need some still more answers. Okay, now continue with one more problem here. Now this is the next one. Consider a packet has arrived with m-bit value of 1 and a fragmentation offset value of 0. Now is this the first fragment, last fragment, or the middle fragment? Definitely you can get a solution for this. When m-bit is 1, it means that there is it could be a first fragment or it could be a middle one. Since because the offset value is 0, now we can easily tell that it is the first fragment. Okay. Now consider this is one more set of problem. A packet has arrived in which offset value is 100. Now what is the number of the first byte? Do we know the number of the last byte? Okay, again you can easily solve this. Like, to find the number of the first byte, we need to definitely multiply that offset value by 8 at the destination. Correct? When we are sending, it is divided by 8. When it has been received, you need to multiply it with 8. Now this means the first byte is byte number, it becomes what? 100 into 8, it becomes 800. Now we cannot definitely determine the number of the last byte unless we know the length of the data. Okay, so first byte you can tell it is 800. Okay, that means the first byte number. Fine. And the last byte you need still more information, like what is the total length, then only you can tell what is the ending data. Okay. Now what if the length is provided? Consider this is the problem where a packet has arrived with an offset value of 100. The header length is 5. Okay, and the value of the total length field is 100. What are the numbers of the first byte and the last byte? Definitely the first byte number, they have given as 100, offset is 100, and multiplied with 8, it would become 800. The total length byte they have given is 100 bytes. Okay, in that the header length is of definitely 20 bytes, where it is 5 into 4. You get it right? 20 bytes, which means that if 20 bytes is an header, there are 80 bytes in the datagram. Correct? So if the first byte number is 800, then 80 bytes. So continuing from 800, the last byte number would definitely be 879. Okay, including 800. So 800 to 879. 879 becomes the last byte. 800 is the first byte. Since we know the total length of the field, including the header length. Okay. Hope you have understood the topics whatever we have discussed about the maximum transfer unit and how the fragmentation is done. Okay, and related to that some of the concepts we have understood. Let us continue the topics further in the next session. Thank you all.